MCM stands for 1000 circular mils. It is a unit of cross-sectional area used to measure the size of electrical conductors, particularly in the context of wire and cable. The concept of using circular mils as a unit of measurement dates back to the mid-19th century. Electrical engineers were developing standardized methods for characterizing the size and capacity of electrical conductors. A circular mil is defined as the area of a circle with a diameter of 1/1000th of an inch. By using this unit, engineers could easily compare the cross-sectional areas of different conductors, regardless of their shape or dimensions. In the context of electrical conductors, the cross-sectional area is directly related to the current carrying capacity of the wire. A conductor with a larger cross-sectional area can carry more current without overheating. MCM became a widely accepted unit of measurement for the size of electrical conductors in the late 19th and early 20th centuries. It is still used today as a standard way to specify the size of larger electrical cables, typically those with cross-sectional areas of 250 circular mils or greater. It is important to note that kmc is not a valid unit of measurement for cross-sectional area. The correct unit is MCM, 1000 circular mils, which is often abbreviated as kcmil. Now let's delve deeper into the significance of MCM in electrical wiring. Understanding MCM is crucial for several reasons. Firstly, it ensures that the appropriate size of conductor is selected for a specific application. Using a conductor that is too small can lead to overheating, voltage drop, and even fire hazards. Conversely, using a conductor that is unnecessarily large can increase costs and make installation more difficult. Secondly, MCM is a standardized unit that allows for consistent communication and comparison of conductor sizes across different manufacturers and regions. This is essential for ensuring compatibility and safety in electrical systems. Thirdly, understanding MCM is vital for complying with electrical codes and regulations. Electrical codes, such as the National Electrical Code or NEC, specify the minimum conductor size required for various applications based on factors such as ampacity, voltage drop, and ambient temperature. MCM is used to express these requirements. Now let's look at how MCM relates to circular mils. A circular mil, abbreviated as cm, is the area of a circle with a diameter of 0.1 inches or 1 mil. To calculate the area in circular mils, you simply square the diameter in mils. For example, a wire with a diameter of 0.5 inches or 5 mils has an area of 25 circular mils. MCM, or 1000 circular mils, is simply 1000 circular mils. So a 250 MCM conductor has an area of 250,000 circular mils. The relationship between circular mils and square inches is as follows: 1 circular mil equals 0.7854 square inches. Therefore, to convert from circular mils to square inches, you multiply the number of circular mils by 0.7854. Conversely, to convert from square inches to circular mils, you divide the number of square inches by 0.7854. Now, let's consider some examples of how MCM is used in practice. Firstly, in residential wiring, smaller conductors such as 14 American wire gauge or AWG and 12 AWG are typically used for lighting circuits and general-purpose outlets. These conductors have cross-sectional areas of less than 250 MCM and are therefore specified in terms of AWG. Secondly, in commercial and industrial applications, larger conductors such as 250 MCM, 350 MCM, and 500 MCM are commonly used for feeders and branch circuits that supply power to heavy loads such as motors, HVAC equipment, and lighting systems. These conductors are typically specified in terms of MCM or kcmil. Thirdly, in service entrance conductors, which connect the utility power supply to the building's electrical system, even larger conductors such as 750 MCM, 1000 MCM, and larger may be required depending on the size of the service and the expected load. These conductors are also specified in terms of MCM or kcmil. Understanding the factors that affect conductor size selection is very important. There are several factors that must be considered when selecting the appropriate conductor size for a particular application. Firstly, ampacity is the maximum amount of current that a conductor can carry continuously without exceeding its temperature rating. The ampacity of a conductor depends on its size, insulation type, and the ambient temperature. The NEC provides tables that list the ampacity of various conductors under different conditions. Secondly, voltage drop is the decrease in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction and reduce the efficiency of the electrical system. The NEC recommends limiting voltage drop to no more than 3% for branch circuits and 5% for feeders. Thirdly, ambient temperature is the temperature of the surrounding environment. The ampacity of a conductor decreases as the ambient temperature increases. Therefore, it is important to direct the ampacity of conductors that are installed in high-temperature environments. Fourthly, the type of insulation used in the conductor also affects its ampacity. Some insulation types are rated for higher temperatures than others. The NEC specifies the allowable temperature ratings for various insulation types. Fifthly, the installation method used for the conductor can also affect its ampacity. Conductors that are installed in conduit or cable trays typically have a lower ampacity than conductors that are installed in free air. The NEC provides tables that list the ampacity of conductors under different installation conditions. Understanding kcmil and its relation to MCM is also helpful. The abbreviation kcmil is often used interchangeably with MCM to represent thousands circular mils. The K in kcmil stands for kilo, which means 1,000. Therefore, 1 kcmil is equal to 1,000 circular mils, which is the same as 1 MCM. The use of kcmil is simply a matter of preference and does not affect the actual size or properties of the conductor. Both MCM and kcmil are commonly used in the electrical industry to specify the size of large conductors. Now let's talk about using conductor size charts and tables. Conductor size charts and tables are essential tools for selecting the appropriate conductor size for a particular application. These charts and tables provide information on the ampacity, voltage drop, and other properties of various conductors under different conditions. The NEC contains numerous tables that are used to determine conductor size. For example, NEC Table 310.15b16 lists the allowable ampacities of insulated conductors rated up to 2000 volts, 60 degrees Celsius through 90 degrees Celsius in free air based on ambient air temperature and number of current-carrying conductors. This table is used to determine the minimum conductor size required for a particular load based on its ampacity. Other NEC tables provide information on voltage drop, directing factors, and other factors that affect conductor size selection. It is important to consult the appropriate tables and charts when selecting conductor size to ensure that the electrical system is safe and compliant with code requirements. To summarize, firstly, MCM stands for 1,000 circular mils, a unit of cross-sectional area used to measure the size of electrical conductors. Secondly, MCM is widely used in the electrical industry to specify the size of larger conductors, typically those with cross-sectional areas of 250 circular mils or greater. Thirdly, understanding MCM is crucial for selecting the appropriate conductor size, ensuring compliance with electrical codes, and maintaining the safety and efficiency of electrical systems. Fourthly, kcmil is an abbreviation for 1,000 circular mils and is often used interchangeably with MCM. Fifthly, conductor size charts and tables, such as those found in the NEC, are essential tools for selecting the appropriate conductor size for a particular application. Consider a practical example to help illustrate how to use MCM in a real-world scenario. Imagine you're designing a feeder circuit to supply power to a large motor in a commercial building. The motor has a full load current of 150 amps, and the distance from the electrical panel to the motor is 100 feet. Firstly, determine the minimum conductor size required based on ampacity. According to NEC Table 310.15b16, a 1/0 AWG copper conductor with 75 degrees Celsius insulation has an ampacity of 150 amps. This would appear to meet the minimum requirement. Secondly, calculate the voltage drop. Using a voltage drop calculator or NEC Chapter 9, Table 8, determine the voltage drop for a 1/0 AWG copper conductor carrying 150 amps over a distance of 100 feet. Assuming a 480 volt system, the voltage drop is approximately 2.7 volts, or 0.56%. This is well below the recommended maximum of 3% for branch circuits and 5% for feeders. Thirdly, consider ambient temperature and dirting factors. If the ambient temperature in the area where the conductors are installed is higher than 30 degrees Celsius, it may be necessary to dirt the ampacity of the conductors. Consult NEC Table 310.15b2 to determine the appropriate dirting factor. For example, if the ambient temperature is 40 degrees Celsius, the dirting factor for a 75 degrees Celsius conductor is 0.88. This means that the allowable ampacity of the 1/0 AWG conductor is reduced to 132 amps, 150 amps x 0.88. Since this is less than the motor's full load current of 150 amps, it would be necessary to increase the conductor size. Fourthly, select the appropriate conductor size based on the derated ampacity. In this case, a 2/0 AWG copper conductor with 75 degrees Celsius insulation has an ampacity of 175 amps, which is sufficient to supply the motor's full load current of 150 amps after derating. Fifthly, verify that the selected conductor size meets all other applicable requirements of the NEC. This includes requirements for conductor insulation type, overcurrent protection, and grounding. In conclusion, using MCM and understanding the factors that affect conductor size selection is crucial for ensuring the safety and reliability of electrical systems. By following the steps outlined above and consulting the appropriate NEC tables and charts, you can select the appropriate conductor size for any application. Remember that kcmil and MCM are used interchangeably, and always refer to the cross-sectional area of a conductor in 1000 circular mils. Understanding the origin and evolution of MCM as a standard unit further enriches your comprehension of electrical engineering principles. It demonstrates the meticulous approach engineers took in standardizing measurements to ensure safety and compatibility across electrical systems. The circular mill's straightforward definition, based on a circle's area with a diameter of 1/1000th of an inch, facilitated easy comparison of conductor sizes. This ease of comparison was crucial in selecting appropriate conductors to prevent overheating and voltage drop, both critical for the efficient and safe operation of electrical equipment. The adoption of MCM in the late 19th and early 20th centuries highlights its importance in managing larger electrical loads as power demands grew with industrialization. The ongoing relevance of MCM today underscores its enduring value as a standard in electrical engineering despite advancements in materials and technologies. As we've covered, KMC is not a recognized unit of measurement, but understanding that MCM and kcmil are the correct terms can prevent confusion and errors in electrical work. Correct terminology is foundational to clear communication and accurate execution in any electrical project. By adhering to standard conventions, electrical professionals can ensure consistency and prevent potential misunderstandings that could lead to hazardous situations. This includes accurately interpreting electrical codes, understanding equipment specifications, and communicating effectively with colleagues and clients. The proper use of terms like MCM and kcmil reflects a commitment to precision and safety, which are paramount in the field of electrical engineering. The knowledge of MCM and kcmil is not just about adhering to standards, but also about fostering a culture of safety and precision in the electrical field. The principles surrounding conductor sizing, ampacity, and voltage drop extend beyond residential or commercial applications. They are equally relevant in specialized fields such as automotive and aerospace engineering, where managing current in confined spaces is critical. While the specific standards and regulations may vary across these industries, the underlying principles of preventing overheating and ensuring reliable power delivery remain constant. This fundamental knowledge equips you to adapt to various electrical engineering environments and to tackle a wide array of challenges involving conductor selection and management. To sum it up, grasp the concept of MCM and apply it responsibly to ensure the safe and efficient operation of any electrical system.